screen?
Yeah.
Yes.
Okay. Okay. Then we can start immediately. The only thing, if you wish, you can also use your cameras. This is also some kind of help me, not just to speak to my screen, but also to have a feeling that I'm teaching students and not the screen. Okay, if you want. No pressure. Okay, then we start. Today is the 10th of October. As you know, this is the course on linear optimization. Just a moment. Yes, this is a course on linear optimization, and we continue our discussion on convexity and separation theorems. And I will recall now a lemma which we started to prove, which we proved almost complete, two items of three, and when we will prove the third one. And when we will continue and actually complete the topic of separation theorems, and go to description of cones. And this will be, okay, we'll see later, but we will need separation theorems if describing so-called normal cones for our admissible sets in linear optimization. Okay, it means our topic now is still separation theorems. In some minutes, I will recall also the separation theorems we had already. But before doing this, let us recall the lemma which we considered last lecture. Yes, last lecture, we had a lemma which said the following, that if we have a set X in Rn, which is non-empty and convex, then they had three statements of this lemma. First of all, the interior of X and the interior of X bar are the same. Again, I recall that this is not true for a general set X, but for a convex set, we proved this. Okay, proof last lecture. Proof last lecture. And then we extended this statement also to the relative interior. We proved that the relative interior of X and the relative interior of X bar are the same. And also this statement was proven last lecture, and it remains to prove the third thing, which is a kind of other way around, that if we take the relative interior of X and consider closure of it, then it is the same as the closure of X. Okay. Before I prove the last thing, question so far, do you understand? Do you remember all the notation? What does it mean if I write rel int X and bar here and all other things? If you have questions, please don't hesitate to ask them.
X bar means complement, right?
Not complement, no. X bar means closure. Complement, complement I would denote by Rn without X. This would be the complement. Okay. And this means closure. Yes, it means, just me recall it here with another color. Yes, closure of set. X bar is X and its boundary. Okay. This is the closure. And okay, you know how to describe the closure in our fashion is the limit of all limits of all convergent sequences in X. Yes, if you take a sequence in X and this sequence converge to something, then the limit point is a point in X bar. Okay, this is the closure of the set. Clear? Questions? Okay. Please be as active in online teaching as you were active in face-to-face teaching. Okay. Concerning the proof, we need to prove proof of free. I just recall I recall the general structure for such proofs. I mean, the logic was that if you try to work with relative interior, then what we do, we consider the affine hull of X, and then we somehow map. You consider linear mapping between Rn and affine hull of X. And of course, all things happen in this affine hull. And then it is enough to prove things just in this affine hull. This is more or less the logic. Okay, let us describe it more precisely. The logic was as follows. We assumed without any restriction, yes, without restrictions, that 0 is an element of X. Okay, X is non-empty, therefore there is at least one element, and we can move this X in such a way that 0 will be an element of X. And of course, this does not change any of these relations. If it was true before we moved it, it will be also true after that and other way around. Okay, therefore, we can, without restriction, assume that 0 is an X. And why does it help? It helps since now, if we have now the affine hull of capital X, this is in this case the same that the span of capital X. Yes, due to sorry, it was some technical issue. Okay, due to the fact that can you hear me still? Yes.
Yeah.
Okay, very good. Okay, due to the fact that 0 is an element. Sorry,
I don't think I can see your screen.
you don't see. Okay, it was somehow okay. But now you should see it again. Yes.
Yes.
Okay, very good. Okay, due to the fact that 0 is an element of capital X, we have that affine hull and the span are the same, and the dimension of this U is of course a linear subspace, and the dimension of this U is some number m, which is less or equal than n. Okay, and of course the case m equal to 0 is not very interesting, and we can immediately check that all statements hold for m equal to 0, since m equal to 0 means that u consists only of the point 0, therefore also x consists only of the point 0, and then it is clear that okay, all these things will be just equal to x, nothing to prove. Okay, and therefore we consider always the case that m is larger or equal than 1 and less or equal than n. And then we did it last time. We considered a linear mapping T, which maps Rm to U. And how we define this mapping, we just choose a basis of U, let's say B1, B2 up to Bm. And our mapping capital T maps a vector Z in Rm to just the corresponding vector in U, which is a linear combination of the basis vectors. Yes, Z1 B1 plus Z2 B2 plus and so on Zm Bm. And we discussed that T is bijective, and also T minus 1, which maps then U to Rm, is of course also linear. Both are linear. And yes, and then we have seen that we can translate the notion of relative interior in Rn to just usual interior in U, in Rm, if you want. Yes, okay, I will write it down again. What we discussed there, they said we have X is subset of U, we know, yes, and then M, which is T minus 1, they can apply T minus 1 of X, yes, this is, this will be a set in Rm, okay? And then we checked last time, the following, that relative interior of X is the same that T applied to the interior of M. And also X bar is the same as T applied just to M bar. Yes, this is what we checked last time, okay? And now this should be clear. If you want, I can make a picture. Probably let me make a picture. If you have, let's say this is R2, yeah, n is equal to 2. This is your convex set, okay, an interval. This is capital X. Oh, let's do it in this way. Here, capital X, such that 0 is an element of it. Then, of course, this line is U, okay? And now we can map this U, as I told you, yes, to just R1. Yes, the dimension of U is M equal to 1. And T maps U just to R to power 1. Yes, it means you have here, I don't know, you have here just line. Okay, and then I don't know, 0 here, and then you will have here in R1, you will have T minus 1 of X. Yes, you will have here this, and this will be the set M. Okay. And then you can imagine, again, this is set X and this is set M, and this corresponds to this, and the relative interior of this corresponds to the real interior of this, and also the closure of this will correspond. The closure of this will correspond to the closure of this, and so on. And this correspondence is by this linear and invertible bijective mapping T. Yes. Okay. Is this clear? This construction? Okay.
Yeah.
Questions you can ask.
Can we go over it once again?
Yeah, sure. What is the question?
Construction. Can you go over the construction?
The general construction, or in the case of the example, what you would like to
In case of the
explain?
example.
In case of the example, okay. In case of the example, again, we have R2, and R2, they have here a convex set. Okay, this is our convex set. Now they consider the affine hull of it, which is also the span. This is this U. And this has dimension 1. Okay, but this U is okay. It has dimension 1, but this is not just R to power something. Yes, it is something different. It is a linear subspace. But of course, there is a one-to-one correspondence between this U and just R. Yes, we can map which direction. Sorry, it was our way around. Yes, it was the mapping was from just R to U. Yes. How we
What confused me.
this was the problem. Sorry, this was the problem. Okay, I'm sorry. Okay, they have a mapping from R1, just from R to U. Okay, we map this to this. Yes. And we have, of course, also the corresponding mapping M T2 minus 1. Yes, they have here the mapping T, and here other way around they have the mapping T minus 1. Yes, and this T minus 1 maps then U, maps U to R, and this T minus 1 maps X to M. Or if you want, T maps M to X. Yes, you have this one-to-one correspondence. And here you have this is the trick. Here you have no other dimensions. And therefore the interior and relative interior here will be the same. Yes. This is probably important to say. Yes. Here for M, interior and relative interior are the same. And then they can work just with usual interior here. And with the mapping T, the usual interior of M corresponds to the relative interior of X. Okay, this is somehow the trick, if you want. Clear now?
Yeah, thank you.
Okay, and thank you for pointing this out. It was just a small mistake. Okay, now our third statement we want to prove that the relative interior of X closure is equal to closure of X. Okay, and by this logic, this is equivalent. This is equivalent to prove just if you take the usual interior of M and take then closure, it is equal to the closure of M. If they can prove this, then they are done. Since by this translation of the result, it is the same. Okay. It means this is what they have to prove. Okay. This is to prove, and then the thing we wanted to prove is also okay. Okay, now how to check this? Again, in both directions. One direction is clear. Okay. What we know, of course, that the interior of M is subset of M, just by definition. And therefore, if you take closure, then you have also that closure of the interior of M is subset of closure of M. This is clear. Here we do not need convexity. This is clear for every set M. Okay, now it remains to prove. It remains to prove that the closure of M is a subset of the interior of M and then taking closure. Okay. We will actually prove following. We will prove actually that even M we'll prove that M is subset of the interior of M and then taking closure. And this is enough since this will directly imply this. Yes, since M is subset of this, then the closure of M will be subset of the closure of this, but the closure of this is again this. Yes. If we will prove this, then this would directly imply that M bar is subset of this. Okay, agree? Okay, now let us prove that M is the subset of interior of M and then taking closure. Okay. How we prove this? Okay, we take, as usual, we would like to prove that this is subset of this. We take just an element Z in M and would like to prove that this is an element of this. Okay. What we know, of course, we know that X is not empty and X is convex. And therefore, we know, you remember it was our first lemma in this subject. Yes, it was a lemma we had last time, or probably two lectures ago, or something like that, that for this case, we know that relative interior of X is also not empty. Okay. But this relative interior of X is nothing else, we said, but the interior of M. And therefore, interior of M is not empty. And also interior of M is convex, yes? Okay, therefore, we know that the interior of M is not empty, okay, and convex. Okay. It is not empty. Therefore, it can take some element there. There is some Z0 in the interior of M. Again, just write down what does it mean. What does it mean? It means there is an epsilon larger than 0, such that a ball of radius epsilon at Z0 is subset of M. Okay. And now what we would like to do. Okay, let me make a picture. Okay, I mentioned this is our M. We have somewhere a point Z0, which you know it is in the interior of M. It means we know there is here a ball of radius epsilon completely in M. Okay. Now we have our point Z somewhere. This is our point Z. And actually we would like Z is from M. And actually would like to prove that Z is here in the closure of interior of M. And we will do it as follows. Okay, of course, we can connect these 2 points. And we know by convexity that every point here on this line is also in M. Yes. Let us write it down. Let T be larger than 0 and less or equal than 1, strictly larger than 0. And we consider ZT, which is equal to 1 minus T Z plus T Z0. Yes. Okay, this is such a point, ZT. And since T is never equal to 0 here, this point is never equal to Z, yes? But it is some point between Z0 and Z, okay? This is the situation. Now I claim that every such point here for every t larger than 0 is also an interior point. I claim that for every such point, I can find here a ball which is completely in M. Yes, I claim that ZT is in the interior of M. Okay. By the way, does the ZT is of course, let me write this down first. By convexity of M, ZT is of course in M for every T. Yes, for every such T. But what we would like to prove, we would like to prove more. We would like to prove that ZT is in the interior of M for every T within 0 and 1. Okay, how to prove this? We need to find a ball around ZT such that it is subset of capital Z or of M. Is clear what I am doing? Please interrupt me anytime if you do not understand any step. Okay. And it turns out that what we can prove that the radius of the ball here will be at least T times epsilon. Yes. The reason for this, the reason is that if you take ball with radius T epsilon of ZT, it will be in M. Let us check this. Let us check this. This is more or less my claim that if I take a ball around this ZT of radius T times epsilon, which is of course also positive, yes, this will be subset of M. Okay, how to check this? Okay, I just take some element y from this bt epsilon of zt. Okay, what does it mean? It means that if the difference y minus zt is then in a ball of radius t epsilon of 0. Okay, do you agree? Okay. Yeah. What is this ball of radius t epsilon of 0? This is of course the same as just t times the ball of radius epsilon around the 0. Okay. And what does it mean? It's also equivalent to say, therefore, that y is in zt plus t times such a ball around epsilon. Okay. And what does it mean? Okay, just again writing out what is zt. This was 1 minus t z plus t z0 plus something t times b epsilon of 0. Okay. Now. No. Okay. What is this? What do you have here? This is nothing else but t times z0 plus b epsilon of 0. Okay. And therefore, this is nothing else but t times b epsilon of z0. Okay. Let me again rewrite this. It means that if we know that y is in bt epsilon zt, then this is equivalent to what? That y is equal to 1 minus t times z plus t times b epsilon of z0. Okay, do you agree? Is an element of. Yes, is an element of. Do you agree? Just a direct calculation.
Yeah.
Okay. Now we know this was our starting point, that Z0 was an interior point, and therefore B epsilon of Z0 was exactly the neighborhood which is subset of M. Okay. Therefore, what does it mean? Therefore, what they have here, what does it mean that Y is an element of this plus this? It means that Y is 1 minus TZ plus T times some, let's say, W, yes, with W in this B epsilon Z0, which is subset of M. Okay, and therefore what we see that, okay, Z was, of course, an element in M, and this W is also an element in M, since this neighborhood is subset of M. And therefore, by convexity, of M, what we have that Y is an element of M. Okay, therefore, what we proved, we started with Y in BT ZT, and then we proved that it follows that Y is an element of M. Therefore, we proved that BT epsilon ZT is subset of M, and therefore we proved that ZT is an element of the interior of M for all T between strictly larger than 0 and less or equal than 1. Okay, very good. And now let us recall what was our goal. Okay, and this, okay, let me write again down what this was ZT. Yes, with ZT equal to 1 minus T Z plus T Z0. Okay. But what was our goal? Our goal was to prove actually that this Z, which we started with, is an element of the closure of interior. Yes. But now what we have? We have that the whole line here, up to the point Z, whole line, is an element of the interior of M. And now it remains to argue that the limit case for T equal to 0 will be an element of the closure. Clear? Okay. How to do this? Just more or less directly by the definition of the closure. Yes, it remains to show, this is actually what we wanted to show, that Z is an element of the closure of interior of M. How to do this? Okay, consider a sequence T K equal to 1 over K. And then for every such T, they get a point Z K, which is when 1 minus 1 over K Z plus 1 over K Z0. What we have that all this ZK by what we proved so far are elements of M for all K. What we also have that ZK converge, of course, for K tending to infinity. What happens? This converge to 0, this converge to 0, the whole thing converge to Z for K tending to infinity. And therefore, by definition of the closure, Z is now an element of the closure of this set. And this is exactly what we wanted to prove. We proved that every element Z of M is actually element of the closure of the interior of M. And with this, we proved what we wanted to prove, that the closure of relative interior is the same as the closure of X itself. Clear? Questions?
No, thank you.
Okay. 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 This was the end of the proof of the lemma we started last time. And now we come back to the separation theorems, and I recall the separation theorems we proved so far, and then we will extend them a little bit. Separation theorems. Okay. We had, let us call it theorem 1. We started with the following. We started with if we take X not empty, closed. Look all the time on the assumptions. They will change somehow. Closed and convex. And Y is not in X. Then we proved that we have strong separation. I will just make a picture. We have our X, our point Y, and here they have a strong separation. Assumptions, closed and convex set for X, not empty. Then we proved the theorem 2. Again, X was non-empty, closed and convex, and Y was a point in the boundary of X. And then we proved there is a supporting hyperplane. There is a supporting hyperplane HAB of X at Y. Okay, all of you remember the definition. The picture is this is capital X, this is the point Y, and they have here this H of AB, the plane which supports X at Y. Yes, it goes through Y, and X is on one side of this hyperplane. This was the second theorem we proved. Then the third theorem we proved was the following. We had two sets, X1 and X2, non-empty, closed, and convex. We assumed that the intersection of these sets is empty. And we assumed that at least one of the sets, let's say X1 is bounded. Under these assumptions, we proved strong separation of these two sets. Again, the picture, you can imagine something like this, 2 X1, X2, and here HAB, strong separation. Okay, this also what we proved last time. Okay, and now, yes, all through these three theorems, yes, already proven. Okay, and now we go a step further. We'll prove 2 more or 3 more theorems. The next one, theorem 4, will be as follows. Let X in Rn, X non-empty and convex, and let Y be not an element of interior of X, then there is a separation hyperplane. What is the difference here to what we had so far? The main difference is here that they have no closeness assumption. Okay, X is now just convex and non-empty. We do not assume that it is closed. Okay, let us prove this theorem. Okay, it's not. They can all the time. They build on things they already know. Yes, and also here they build on what we already know. They consider the first case, case one, that okay, we know so far just that y is not in the interior of x. Okay, but assume that y is not in x bar. Now we can apply our very first theorem. Yes, x bar is closed. Yes, we know, of course, okay, since x bar is closed and of course convex. Yes, we proved that the closure of a convex set is again convex. We can use theorem one. Yes, theorem one was, let's go back, was the separation between a closed convex set and a point which is not an element of it. Okay, and this would be exactly here the situation. Y is not in X bar, then they can use theorem one, which gives us the existence of a hyperplane HB. This hyperplane separates Y and X bar. And of course, therefore, it separates also, Y and X. Yes, since X is subset of X bar. And therefore, in this case, they are done. Okay? Please, again, if you do not understand the logic somewhere or on some one argument or something like that, please interrupt me and ask. Okay? Okay. Okay, now the second case. The second case, now they have to assume that Y is an element of X bar. Yes. By assumption, they know that Y is not an element of the interior of X. Yes. This is what we assumed here. Y is not an element of the interior of X. Okay, Y is an element of X bar, but not element of the interior of X. And here we can use one of the items in our previous lemma, that this interior of X is the same as the interior of X bar. Yes, by previous lemma, since X is convex and not empty. Okay. Now what they have that what is the situation? The situation is that Y is in X bar and Y is not in the interior of X bar. What does it mean? It means, okay, the set, for every set, the closure consists of the set of the set itself and the boundary. What they have here, if they have some element which is in X bar but not in the interior, what does it mean? It means that Y is an element of boundary of X bar. Do you agree? It is not. It's in X bar but not in the interior. The only possibility it is in the boundary.
Yeah.
Okay. Now we can apply our theorem 2. What was the theorem 2? Theorem 2 was exactly the situation. They have a closed convex set, yes, now X bar, which is closed, and an element which is in the boundary of it, yes. It means that we can apply theorem 2, which gives us the existing of a hyperplane HAB, which supports X bar at Y. Okay. And of course, this is also a separation plane, separation hyperplane for X and Y. Okay. End of the proof. Okay. Okay. And now it's interesting. Now you see that they removed the closeness assumption. And now probably you remember how was our proof for two sets. Our proof for two sets was as follows. We considered the difference of this set of these two sets and tried to separate this difference from zero. And the difficulty was there to prove that this difference is closed, yes? And we discussed that difference of two closed sets is not necessarily closed. They had a counterexample and so on. And then using boundedness, they proved that it is actually closed and we could apply things. Now we have removed this closeness assumption, and therefore we can much more easier work with two sets. We will do not need boundedness anymore, and of course closeness also not. And therefore we can prove now a stronger theorem, theorem 5, which says just let x1 and x2 both in Rn be non-empty and convex, and let x1 intersected with x2 be empty. Okay, but you see no closeness assumption, and also no boundedness assumption anymore. Just two convex sets, general convex sets, non-empty with empty intersection. And then the theorem says then there is separation hyperplane. The proof now is quite easy, but we will do the proof. After the break. Yes, this is a good idea. I think they make now a break of 10 minutes, and I see something here in chat. I see a question in chat. It is supporting plane for X bar, but it is some other type of separation for X, which is subset of X bar. What was the question? The question was probably, I mean, I do not really always read the chat, and therefore it is better to ask questions just directly interrupting me. But the question is probably here, yes, that if this hyperplane supports X bar, does it mean that it separates X and Y? Okay, let us briefly try to understand this.
Hello, can you hear me?
Yes, I can hear you.
Yeah, the question was about that.
About this, yes? Let me answer this question. Okay, what we know? We know that HAB supports X bar at Y. What does it mean? It means that Y is an element of this hyperplane, and X bar is on one side of this hyperplane. It means in H, let's say, less equal AB. Okay. But now what does it mean? Of course, since X is subset of X bar, what they see that also X is in H less or equal AB. And therefore, by definition of separation, this hyperplane separates Y and X. Not strongly or not strictly, but it separates. Okay? Does it answer your question?
Yeah, I get it. So I was wondering whether it was some kind of stricter separation because X was subset of X.
Exactly, and therefore we have just, the statement is just that there is a separation hyperplane. Okay, now let me make a break, 10 minutes. In 10 minutes, I will be back and we will continue. You can also prepare more questions. See you in 10 minutes.
Okay, goodbye.